Hello sir, today I'm gonna introduce about the RLC circuit analysis by using the ODE. So the objective is understand how component like resistor, indicator, and capacitor interact and how ODE help us to predict their behavior over time. So this is our very simple RLC circuit. So beside them, this is our value example as an example. So the first step will be the KVL. So as you know, the KVL is total voltage across all components equal to the applied voltage, which is Vt equal to Vr plus Vl plus Vc. Then we have the resistor formula, which is Vr equal to R times I. And then the indicator will be Vl equal to L times Vi over dt. Then the capacitor will have it I over C times integrate IT. Then we substitute all this expression into these KVL formulas. Then step 2, we will derive the ODE. So in step 2, we will need to differentiate. After we sort inside all this expression into this formula, then we need to rearrange it to the ODE form. So after we do that, we need to derive our Vt. So after we derive our Vt, which is the 5 sine 2t, we'll have the dz over dt equal to 10 cosine 2t. So the ODE will become d square I over dt square plus 10 times di over dt plus 100i equal to 10 cosine 2t. Then we'll go to the homogeneous solution. The homogeneous solution equation is the d square I over dt square plus 10 times di over dt plus 100i equal to 0. Then we let the di over dt equal to lambda. So the lambda square, so it will become lambda square plus 10 lambda plus 100 equal to 0. Then we solve this by using the quadratic function as a quadratic equation. After we solve this, we can see that our lambda is equal to negative 5 plus and minus I square root 75 and also equal to negative 5 plus and minus I5 square root 3. So as you can see, it is distinct root. So as what we can see in the formula sheet, when we have the distinct real root, we'll have the general solution of the first general solution as shown in the formula sheets. Then we go back to our homogeneous solution, we'll have this homogeneous solution as our as our homogeneous solution. Okay, so the particular solution for forcing term 10 cosine 2t assume that a particular solution of the form, so I equal to a cosine 2t plus b sine 2t. Then substitute this into original equation, then compute the derivative, which is the di over dt equal to 2a negative 2a sine 2t plus 2b cosine 2t. And then we differentiate again, we have the d square I over dt square equal to negative 4a cosine 2t minus 4b sine 2t. Then we substitute both of these differentiation equation into the solution. We have the ODE solution, which is this form. So after we substitute, we'll have this whole formula. It's a bit long, so I won't read, so I don't read it out. So we group the terms for cosine 2t and sine 2t. So the coefficient of cosine 2t will be, we'll have negative 4a plus 220b plus 100a equal to 10. And then we simplify it, we have the 96a plus 220b equal to 10. Then the coefficient of sine 2t will have negative 4b minus 20a plus 100b equal to 0. Then we simplify it, we have negative 20a plus 96b equal to 0. Then now we have the last step, the total solution. Combine the homogeneous and particular solution together. Then we use the initial condition, which is I equal to 0 when and then di over dt is also equal to 0. Solve for C1 and C2. After we finding a, b, c1 and c2, we can write the final expression of I. Then we plot the result by calculating the value and then plot the graph of. So the graph will be shown as the figure is shown inside the presentation slide. Okay, so thank you for the present listening the presentation. It's a bit noisy due to my laptop problem.